In this lecture video, I'm going to talk about disks and input-output devices, something to do with the third main objective of an operating system that we have discussed before. That is the concept of persistence. So we promised that we're going to talk about all these features in detail in all of these lectures, and now it's time to talk about persistence. So basically, what persistence means is that we need to have a way of saving data. We need to have a way of communicating with disks and also input-output devices. So now let's look at how all of that works. So basically the bottom line is that an operating system needs to enable storage and retrieval of persistent data, and that is what we mean by persistence. So we need to be able to use some disk management system and to offer a service to move data around this system. Actually, the term we should use is input-output control, because not all devices are RAM memory, so memory management is not really an appropriate name anymore. So input-output instructions basically are instructions that control how different devices are mapped to certain ports. And you might remember from previous lectures the idea of memory mapped input-output. So we have devices that are controlled using registers, which are extensions of the system memory or RAM. And the operating system sees these registers like any normal memory segment, except that they actually control the various input-output devices. Both of these approaches, I/O instructions and memory mapped I/O, are equally good. Depending on the device and architecture, we could see either one of these used in practice. Why I/O devices and their control is important? Well, if we look at the different connections from the CPU to different devices, you can start to appreciate the complexity. So there might be some graphics adapter which needs I/O control. Also some memory also needs I/O control. These are devices that connect directly to the CPU. And then there is a set of different I/O devices that are controlled by various I/O chips. These might include network adapters, disk drives, keyboards, mice, or other USB devices. So it would make sense to have some sort of I/O controller to manage all of this complexity and to have some sort of common way of communicating with the CPU. That standard way of communicating between I/O devices and a CPU is called a canonical device. A canonical device is an ideal model of a device which basically dictates what a hardware interface needs to look like. So this ideal device has a state, as in a status register, some given instruction or a command in a register, and also a data register. So basically what the operating system does with this canonical device or canonical device driver is that it reads and writes to these three registers, and then what actually happens inside of the device doesn't concern the operating system. So as long as the device, whatever it is, if it's it doesn't matter if it's a disk drive, it doesn't matter if it's a keyboard, as long as that device implements an interface that looks like this, well, then it can communicate with the operating system, and the operating system doesn't need to know how that device actually does what it is that it does. The operating system then should poll for the status of this device to see if it's ready to do something. And when it's ready to receive instructions, the status register changes its value to signal the operating system. So the operating system can basically read the status register and determine what is the state of this device through this interface. In practice, however, that model wouldn't work because polling is actually slow. So the operating system, it turns out, it has better and more important things to do than to poll all the auxiliary devices and ask what they are doing. So what they actually do is they call hardware interrupts to signal the operating system when some operation has finished. On the other hand, at some points, we might want to check on the status of a device so that status register is there for a reason. In some other cases, the operating system or CPU might sometimes be concerned about the operation of some device. For example, if this graphics unit needs to tell the monitor what to draw, or when a memory controller is copying something from the system memory to the disk cache. So for example, in these situations, it is beneficial for the operating system to actually know what devices are doing before issuing new commands. The problem of polling in its bare essence is the following. So when the CPU is waiting for a device, say a disk, it's unable to do anything else except polling or to give another process the execution context. On the other hand, a hardware interrupt every time a device has new input-output activity wouldn't work either. Imagine, for example, if a network adapter were to call a hardware interrupt every time there is some traffic in the network. So in reality, this would happen all the time because of the network protocols, and this would end up in somewhat with a live lock, an internal denial of service attack against the CPU. With polling, the decision making happens at the operating system's end. So every now and then, the operating system could ask for new data from devices, and other times it would accept interrupts. So in practice, a so-called hybrid approach is the best. Hardware interrupts can also be bundled together, which is so-called coalescing. So multiple interrupts that are processed in a bigger batch. However, this approach would increase latency, which is not preferred. So it would increase the time in which an interrupt would be processed. There is also another way of reducing the number of programmed input-output requests. That is what is called direct memory access. So here, programmed I/O means the situation of when the CPU is in direct control of some device. That is when the CPU is actively polling for the status register of some device. So direct memory access is a tool, or more like a protocol, that different devices can implement, where the tool, the direct memory access, reads a memory address from the processor along with the length of the data that is supposed to be processed, and the name or address of a target device to which we are currently writing or reading from. And then DMA handles the writing in the background, and it raises an interrupt when writing has finished. Meanwhile, the CPU can do something else. So basically, if we were to draw it as a picture, so let's imagine we have process 1 here executing on the CPU, and whenever process 1 needs to write something to the disk, it transfers that writing task to DMA. The CPU can meanwhile change context of execution, while DMA figures out what to write to the disk. And meanwhile, some other process is being executed on the CPU, and simultaneously the data from the previous process, the one that wanted to write something, is being written on the disk. And once this task has completed at this point, when DMA signals the CPU that the writing task has finished, that's when the first process gets to continue execution again. So to summarize, there are different ways of controlling devices. The devices might have different interfaces. And the idea behind all of those ways to control the devices is the same. So build some middleware, often called a driver, to harmonize the device's I/O interfaces over the different hardware interfaces. So basically make the different devices look the same. This is the same idea as virtualization. So like with virtual processors or virtual memory, the idea is to end up with a collection of simple interfaces which can be updated or re-implemented afterwards. And the devices are none the wiser, they only see what is this virtual interface. And this is the a more abstraction approach, as in we hide device details behind some abstraction. As an example of what abstraction looks like when it comes to device drivers, let's look at something like a Linux disk driver. So from the programmers or applications point of view, there is an abstraction, a interface called the Posix API. The Posix API is a collection of programming libraries that have functions such as open, read, write, close, etc. And when we are writing a program and application for the Linux operating system, we can use these functions to open and close files, to save and to save data and to read data. This is only the top of the iceberg. So there is behind this Posix API, there is another abstraction, which is the file system. And behind the file system, there is an API or an interface called generic block interface. So a generic programming interface where programs are able to read and write blocks. Below that, there is a generic block layer. And there is a specific block interface, so a protocol specific read-write library. And bottommost there is a device driver, and this depends on what kind of device it is. If it's a SCSI drive or an ATA drive or a SATA drive, and anyway, this is very far removed from the actual application itself. So this is an example of what this different abstraction looks like. So these different APIs or interfaces in between handle communication between these different layers of abstraction. Finally, what are the important things to remember from this lecture? Well, first of all, the basic operating principles of an I/O device and the idea of the canonical device. And secondly, we looked at an example of what a disk driver looks like in Linux, and what its interface looks like, and what are the and how many layers of abstraction there are.